Assalamualaikum warahmatullahi wabarakatuh and a very good day everyone. Today I would like to explain regarding tutorial on optical power budget. Okay, let us first see exercise 1. Design a cost-effective optical fiber link for transmitting 20 megabit per second for a distance of 0.7 kilometer using the components given in this table. Okay, so this is the table. The photodetector given in the design has a sensitivity of negative 27 dBm. The link requires a connector with a loss of 1 dB, a source coupling of 2 dB, and splice losses of 4 dB. The first question asks you to choose the suitable components for the design and justify your answer. For the first question, you need to know what is the distance of this fiber link. And you can see that the distance is only around 0.7 kilometer, which can be considered as short distance. So for short distance communication, you just need to use LED. Okay, because LED is for short distance, laser is for long distance. Okay, so besides that, the advantages of using LED is that it is lower in cost as compared to the laser. Okay, so since we are using LED, meaning that our suitable fiber would be the multimode fiber. And if you look into the wavelength, which is 850 nanometer, we need to use the same wavelength for the fiber, which is also 850 nanometer. So the most suitable fiber would be the first fiber, which is this glass step index fiber with loss of 5 dB per kilometer and wavelength of 850 nanometer. Okay, so that is the suitable component to be used for this design. The second question asks you to verify the design by using power budget. Assume a safety margin of 6 dB. Okay, so for this type of question, we need to use the equation for the power budget. As I've mentioned before, you can just use this formula. Sorry. Okay, so the formula for power budget is power margin. Okay, power margin must greater or equal to 0. Okay, and the equation for power margin is equal to power transmit minus power received minus all the related losses minus safety margin. Okay, so if safety margin is not given, you just need to ignore it. Okay, so in this case, our power transmit is from the light source, okay, which is 0.1 milliwatt. So this is our power transmit. Our power received is actually the photodetector sensitivity, which is negative 27 dBm. So this is our power received. The losses is the connector loss, which is 1 dB, okay, which is here. The source coupling loss 2 dB, the splice loss 4 dB. Okay, the safety margin is 6 dB. Okay, so there are some law that you need to know before we proceed. Okay, so by now you should know how to convert from watt to dB and to dBm. Okay, for example, 1 watt is equal to 10 log 1, which is equal to 0 dB. Okay, and if you want to convert into dBm, you should know that the formula is equal to, if it is 1 watt, it is equal to 10 log 1 divided by 1 milli. 1 times 10 to the power of negative 3, or just 1 milli. Okay, so you will get, this one you will get what? 10 log 1 divided by 1 milli, which is equal to 30 dBm. Okay, so this is 30 dBm. Okay, so from here, actually you can straight away convert from dB to dBm. Okay, so let's say you want to convert something from dB to dBm, you just need to plus 30. Okay, if you want to convert from dBm to dB, you just need to minus 30. Okay. For example, you have 4 dB. Okay, 4 dB. You want to convert into dBm. Okay, you want to convert to dBm, right? So you just need to 4 plus 30. Okay, so 4 plus 30, you will get 34. Okay, so that's how to convert straight away or in a faster way. Just use the formula here, this and this formula. Okay, so another things that you should know before we proceed with our calculation is that I always prefer you to convert all the values in dB. Okay, if let's say you have a dBm here, negative 27 dBm, convert it into dB first. Because when you are doing the operation of dB, no matter it is plus or minus dB, the answer will still be dB. Okay, but if you are using dBm, if it is minus dBm, your answer would be dB. Okay, so this one will be a bit difficult for you to remember. So that's why I suggest to you to just use this. Okay, convert everything into dB and do the operation as usual. Because dB plus or minus dB is still dB. Okay, so after extracting all the formula or all the values from this exercise, you will obtain this. Okay, so the photo detector sensitivity or the power received is negative 27 dBm. If we want to convert from dBm to dB, we need to minus 30. Okay, negative 27 minus 30, you will get negative 57 dB. Okay, this is our power received. Okay, our power transmit 0.1 milliwatt. If we convert into dBm, you will get negative 10 dB, 10 dBm. But if you want to convert into dB, you will get negative 40 dB. Okay, so these are all the losses. Okay, the connector loss 1 dB, source coupling loss 2 dB, splice loss 4 dB. And don't forget the safety margin 6 dB. Okay, we also have the fiber attenuation or fiber loss, which is 5 dB per kilometer. And since our link is 0.7 kilometer, we just need to multiply the attenuation loss, the attenuation coefficient with the link distance, which is 0.7 kilometer. Okay, and you will get 3.5 dB. Okay, this is the fiber loss. Okay, so we already know this formula, power margin must greater or equal to 0. And we also know that we have the formula of power margin equal to power transmit minus power receive minus the losses minus the safety margin and equal to this. So power transmit is negative 40 dB. Power received is negative 57 dB. Okay, these are all the losses. Okay, connector loss, source coupling loss, splice loss, the safety margin, and this is the fiber loss. And finally, you will get 0.5 dB. So this is our power margin value. So you can see here that our power margin value is greater than 0. Greater than 0 dB, meaning that this system is viable. Okay? Okay, let us look into the second exercise. The following parameters are applied for single-mode fiber long-haul communication operating at wavelength 1.3 micrometer. Mean power launch from the laser transmitter is negative 3 dBm. Cable fiber loss 0.2 dB per kilometer. Splice loss 0.1 dB per kilometer. Connector loss at the transmitter and receiver with 1 dB each. Mean power required at the APD receiver is given by this. When operating at 35 megabit per second, it is negative 55 dBm. When operating at 44 megabit per second, it is negative 44 dBm. Safety margin 7 dB. Determine the maximum possible link. Okay, the length of the link without repeaters when operating at 35 megabit per second. Okay, so for this type of question, the question actually wants you to find the maximum possible link length. Okay, what is the length of this design? Okay, the maximum length of the link. Okay, and you can see that the system is operating at 35 megabit per second. So meaning that we will only use this power received. Okay, negative 55 dBm. Okay, so don't look into the this one, negative 44 dBm. Okay, because that is for 44 megabit per second. Okay, the system with bit rate of 44 megabit per second. Okay, so from here, we will still be using the same formula. Power margin must be greater or equal to 0. Okay, so since the question wants you to find the maximum link length, then we will use power margin equal to 0. Okay, and we also have the formula of power margin equal to power transmit minus power received minus all the losses minus the safety margin. Okay, and this one is equal to 0. Okay, so let us proceed. So these are all the parameters that I have extracted. Okay, so if you can see here, power transmit, I have converted from dBm to dB. Okay, so from dBm to dB, I need to minus 30. Okay, minus 30 minus 3, you'll get minus 33 dB. Fiber loss is 0.2 dB per kilometer. Splice loss 0.1 dB per kilometer. Connector loss 2 dB. Power received at 35 megabit per second is negative 85 dB. Okay, I've converted the negative 55 dBm into dB, and the safety margin say 7 dB. Okay, so the question wants you to find the maximum possible link length at 35 megabit per second. So let's say the length is L. Okay, so if let's say the length is L, we need to find what is the value of L. Okay, so we already know that we have to use this formula, power margin equal to 0, because we want to find the maximum link length. Okay, and we have all this data. We have the values of power transmit, we have the power receive values, we have all the losses, except that we don't know what is the length of this. And this one is equal to 0. Okay, this is the power transmit, negative 33 dB. This is the power received. This is the fiber loss. Okay, so you can see the fiber loss is 0.2 dB per kilometer. Okay, if I multiply this with the value, which is in kilometer, okay, the L value is in kilometer, right? Okay, you know that the unit is in kilometer. Actually, this kilometer and this kilometer will be cancelled. Okay, so I will get 0.2 L and the unit must be in dB. Okay, so that's how I get my 0.2 L. Okay, I get this one, the fiber loss. Same things goes for the splice loss, 0.1 L dB. Okay, because the L is in kilometer. Okay, so by simplifying this equation, I will get 45 dB minus 0.3 L dB equal to 0 dB. Okay, so 45 minus 0.3 L equal to 0. Just simplify this and you will get L equal to 45 divide 0.3, which is equal to 150. Okay, remember that your L, the unit is in kilometer, so you just put kilometer here. Okay, so your length or link length is the maximum link length that it can go is 150 kilometer. Okay, so I think I would like to stop now. Thank you everyone. Assalamualaikum warahmatullahi wabarakatuh.